All right. Okay. Thank you all for coming. So today our speaker is Vincent. So Vincent got his master's degree in 2011 from National Taiwan University with the thesis on thermoelectric transporting bilateral fin. And after that, Vincent went to TSMC, Taiwan Semiconductor Manufacturing Company, to work as an IC integration engineer. And then in 2014, Vincent joined us at Rutgers and has been working with Professor Michelle Christensen in condensed matter experiment. So his PhD thesis proposal is about fault tolerant and superconducting qubits. So today, and Vincent will give us a talk on this marching toward quantum readiness. I think he kind of gets inspired by his intern at IBM recently. So I guess Vincent has lots to talk about. So let's first unmute ourselves a bit and give Vincent a big hand before the talk starts. Okay.
Thank you.
Thank you so much. Okay, let's take it away, Vincent.
Okay, thank you, Tsung-Chi. So my name is Wen-Sen, and I'm a condensed matter student, experiment student, and a Q-skid advocate. And before we start, I would like to correct one typo in Tsung-Chi's kind advertisement about myself. I'm far from an expert even in my research field. We are more like, we call ourselves quantum wrangler who would like to use our spare time to help publics to harness the power of quantum computer. And so let's get started. So today my topic is about marching toward quantum readiness. In echo with the recent, or actually it's been a year ago since Google published this quantum supremacy. So one common question that people ask is quantum really ready for initiate an industry? And today's talk is my 2 cents about addressing this question. So if we look back, so this is very similar to any talks that you'll hear from quantum computing. So we always compare about the history of classical computer. And here I list some major milestone, basically focusing on the development of IC chips, specifically for field effect transistor. So around 1947, field effect transistor are realized. And after about 25 years, at 1971, we have this first, the metal oxide semiconductor large scale integrated circuit. So MOS LSI 4-bit chip, Intel 4004. And after another 17 years, we have the baby of the classical computer, this IBM System I, with CMOS technology and VLSI process. And if we kind of like just, you see this red bar is about 25 years, we just shifted to the beginning of 1998, since the proposal of charge qubit. We're kind of, if we extrapolate this thing, we're kind of around the corner where we start to have, about to have the first quantum bit, like quantum processor, let's put it this way. We're expecting to see it in the near future. And in fact, that's just for superconducting qubits. And recently we're also having many other platforms like Honeywell. They're like proposing this ion, trapped ion system with also comparable computing power. Now we're using this quantum volume as a metric to gauge how good the quantum computer is. And they are comparable to IBM's superconducting qubits. And we're seeing more, like for example, Intel, they're working on silicon quantum dots, and Microsoft, they're focusing on this fault-tolerant topological quantum computings. And more recently, there's a British company, they're proposing this full photonic circuits that can be also used in quantum computing as well. So we're seeing much more. And actually, I would like to point out that the technology progress was not only driven by this research interest in quantum systems, but also by the demands or like the applications. So if we look back, the first version of the computing elements vacuum tube people wasn't very interested until Turing machine was proposed. And after that, once we have this field effect transistor, there's a bunch of different progress. And in terms of, for example, making it as a computer or even a game console and stimulate each other, which eventually between the software and hardware, we start to have exponential progress. So what I would like to point out here is, even though superconducting qubits might not be the final platform, with all these demands we're having now, for example, virtual reality, augmented reality, 5G network, cloud-based, machine learning, or even the most recent Edge AI, which includes the self-piloting drones, self-piloting cars. All of these demands will stimulate the progress of quantum computing. So I would argue this way: instead of asking, is quantum ready? I think we should be asking what must be done to be quantum ready for the whole generation, for example. The reason is we are looking at something like 10 or 10 to 50 years for full-scale quantum industry. And one important thing is we want to prepare the future quantum workforce in advance. And but more importantly, we want to prepare in the right way. What do I mean by that? Is we probably want to, for example, start to educate students, for example, high school students, or not just grad school students, but also high school students and undergrads. Start to teach them some quantum computing, some sense of quantum computing. But you might be wondering, so for example, myself, right? I'm not even learning the computer in the right way in my high school. So this is what I learned in my high school when I working on the computer classes. We basically play video games, right? And so now you're asking me to teach high school student quantum computing, or just like it's a joke or something. It's actually a little bit more subtle than that. So if we look back into the history of the computing industry or even high-tech companies, what we keep seeing is in terms of distribution of race, we have a white male, they are always dominating in this industry. And since this industry is high profit industry, you get a lot of money, get a high salary, and they will give you a more in terms of advantage when you're teaching your next generation, and your next generation will able to rejoin this industry. And as a result, it's become extremely difficult to flip the whole generation. Like, so for example, we have the data we're looking at now is pulled out from this website, this link. And what we're seeing here is the data since 1991 to recent 2016. And the number of white males, they are dominating all the way. And recently the differences are getting better and better, but still the distribution is still very different. From where I came from, Taiwan, we don't have like that much race differences, but we do have a dramatic difference, like contrast between low working class and the medium class. So, for example, myself, I do undergrad, and then so basically I do high school and undergrad. But there are many people, they are just able to they can only afford the tuition of high school, for example. So they need to find a job after they graduated from the high school, and they can only work as a operator in a semiconductor foundry. And myself, because I'm able to pass those tests, and I'm able to get to an engineer job, which had double the pay of them of those people just have only high school degrees, and they need to work like twice as long as I do, but get half the payment. So it's kind of unequal situation. And under those situations, their next generation will be will have less resources. So the whole situation is difficult to turn. So so here I
Hey,
kind
Vincent,
of
I have a question. Hi, Vincent.
yeah, sure.
For the previous page, can you this
Yes.
this one? Can you go back one slide? Yeah.
One
so
more?
what's like the two figures on below? Oh, the next one.
The two figure on the below?
No, the next one.
Oh, you mean this one?
Those two small figures. What does
This one
tell you? Yeah, I cannot.
Oh, this is
see
basically
clearly.
the sorry, yeah, I should put it back more.
I
So
cannot
basically,
see
it's just like in terms of populations. So maybe I'll just let me do this. So basically, this is the like the distribution and this function of time. So that this bar is in terms, sorry, not this function of time, but it's like distribution between different measures. So what we're seeing here is, for example, around this time, 1991, 92, the white population, they are almost CS measured, and the rest of the degree are, sorry, this is by races. Sorry, this is 83% is the percentage of the by the entire group. So they have 84% of people in the U.S. are white race, and white people, and they're 83% of them. 83% of the computer science majors are white people again, and there's 70% of them are white people among all degrees. And that kind of answer your question. And these days they're more evenly distributed, but still the numbers are there's still a huge gap between the populations, between the races.
Got you. Thank you. Great.
Okay, thank you. So there are some solutions that I can think of as of now, and please definitely let me know if you come up with more ideas, so we can discuss. So the first three are just naturally came up to my mind is we want to lower the financial threshold to enter this industry. So basically the idea is, okay, we're seeing this problem in the past. So we have this classic computer and the classic computer industry, and some people got got some advantage, jump into this field earlier, and their generations are able to benefit from this high profit industry and get a better life, get a better education, and they can come back and rejoin this industry. And if now we're imagining a new quantum industry, so what can we help to like correct this at the beginning? So that's the main backbone of my talk today. And so the first three is natural. We want to lower the financial threshold so people with less resources, they can afford it. And second, we want to lower the technical threshold. So basically, it should be as simple as you just click install and next, and you can start to play with this quantum computer. Right? You don't need a lot of technical things. And third is a mobility ratio, like this suburban and city, they should have the similar accessibility to the material should be accessible. The best way is just online, right? As long as you have the internet, you can access the educational material. And number 4, I was thinking is we want to lower the knowledge thresholds. So we are, so for example, myself, I learned quantum physics since undergrad, and then a master's degree I learned again, and then PhD degree I learned it again. And in terms of quantum information, there is probably not that much knowledge that people need to learn. For example, what we're seeing now is software engineer. They don't need to know anything about silicon. They can do the job pretty well, right? So if we have an industry, I would imagine there will also be some quantum software engineer that they don't need to know what happened in terms of hardware. Like, for example, they don't need to know Josephson junction that we're using now. This superconducting circuit we're using now might not be the eventual platform that people can use. So they don't really need to know those like solid state physics. And the 5th one is lower the interest ratio, because quantum computing, as we all know, we're grad students, and we know that sometimes it can be very boring or even really tough in terms of, like, for example, for myself, the equation and mathematics is kind of like the bottleneck when I learn quantum physics. Right, so QSK kind of able to address the first 3 because first of all, it uses Python interface, so and it's fully online, so through these cloud services. So basically, QSK is a great candidate to solve the first 3 problems. And here I list some of the applications on this slide. So feel free to let me know if you want to know more in learning QSKit. Basically, what we're able to use now is you can use QSKit to operate the quantum computer for single qubit gate operation, multiple qubit entanglement operation, and some transpiler functions. Basically, change the. So we're still in this so-called gate-based quantum computing. So we have many gates, and we want to transpile the gate into a real microwave pulses in the superconducting circuit. And we can represent and visualize the block sphere. We can visualize the molecular dynamics. We can do variational quantum eigensolver problem, and also some optimization problem. This is what QSKit or superconducting quantum circuits we're able to kind of solve it now. All right. So
yeah, it's a question.
Now this is the 4th point. Yeah, sure.
So for like all these things, previous slide. So for all these things, is that so classical computer cannot do all these things?
That depends, because actually we're able to use this so-called simulators, classical simulators, to do this work. They're all possible. They just like take some times, but since now classical computer is pretty advanced, so we just put it into supercomputer, for example, and you can still solve it in a reasonable time. There are some problems that quantum computer does demonstrate advantage, and it's actually, we can actually count it by a single hand. There is only like three algorithms. One is a Grover algorithm that can perform unstructured search, and also this vectoring problems by Shor algorithm that basically provides some. Basically, we're only comparing like n versus square root of n differences. There are not that much accelerations, but the problem is if we can. The problem is we don't even have a idea how to operate the quantum computer in the right way. So it would still require more efforts to develop new quantum algorithms to attack the problem accordingly. Yeah. But now, to your question, everything can be solved classically still. Yeah.
Oh,
With some longer time. But yeah.
Also go back one question, like, so you at first you mentioned there are many companies, they use like ion traps, they use superconducting qubit, they use topological material, topological quantum computation. So so first, like, which one is like the best now, and which one seems most promising?
The most mature one is still the superconducting circuits and trapped ion system, and now they're able to. So basically, later on, we'll show you some kind of quantum circuit that are in terms of software. Like I just coded some 2 qubit gates, for example. But basically, what we need is single qubit gate and 2 qubit gate. The idea is like in the classical gate, we have AND gate and we have NOT gate, and we can, based on some, I forgot what's the theory behind that, but as long as we have AND gate and NOT gate, we're able to come up with all these logic operations. And in quantum circuits, we're kind of hope that we need some kind of single qubit gate and 2 qubit gate. So these are the 2 fundamental building blocks in the supercomputer and in the quantum computer. And currently, superconducting qubit has it, and trapped ion has it. Silicon quantum dots, they kind of have a 2 qubit gates, but it's not as reliable. And the rest of them just don't have a 2 qubit gate yet. So in terms of like how mature it is, but again, this is all based on gate-based quantum computing. There could be other kind of some kind of other architecture that can do the computational works, but we are just kind of extrapolate what we understand so far from classical computer, because gate-based it worked pretty well. So we just extrapolated and imagined that in quantum computer we also want some kind of gate that can do logical operations. Yeah. The one idea just like we imagine how do we do plus, like we have 2 input A and B, and we have AND gate, and we have some NOT gate, or for example exclusive OR gate. And if I'm allowed to do that, how can I do A plus B? So A plus B, the least significant digit is, for example, you want A plus B, and the least significant digit should be following the operation of exclusive OR, right? Because 0 plus 0 is 0, 0 plus 1, 1 plus 0 is 1, and 1 plus 1 is 0, because you want overfill to the most significant digit. So the least significant digit is 0. It should be exclusive OR. And the most significant digit should be AND operation, because 0 plus 0 is 0, 1 plus 0, 0 plus 1 is also 0, and 1 plus 1 is 1. Like you have I'm not sure how to use in English. 进位英文怎么讲？就是 basically you have overfill to the most significant digit. So basically, this is the idea how you start from some logic operation, and you get some mathematical operation plus, for example. And similar things happens in this classical computers. In the quantum computers, you want some gate, and this gate, superconducting qubits and ion trap, there are 2 major candidates so far. We have successful gate-based quantum computing.
Thank you. Great.
Thank you. Okay. Delay. Okay. So one idea so now we're addressing the 4th question, how to lower the knowledge threshold. So what I'm thinking is actually we should do some buzzwords pools, basically just some. So this is the some just quick study that I do. I basically pull out the what is how you call that, the this So I go to the website, those quantum computing education websites, and pull out the hotkey, all of the vocabulary they used, and then do some statistics and generate this character, this word cloud. And so what we're seeing here is people tend to so this basically those keywords shows up frequently, like for example operators, algorithm, computation, classical, and you won't see like Josephson junction here. There's nothing like Josephson junction or ion qubit. So Trappist ion qubit, for example. What you're seeing here is more like software thing or like architecture things. So you have protocols, you have no copying, or like some fundamental things. So this gives us an idea the current interest in terms of educational efforts or industry efforts. We're more towards software and how to use it instead of the fundamental, like how do we really realize the qubit operations, for example.
I got a question for you,
yes,
Vincent.
please. Yes.
So, I mean, this is interesting because you talk about the quantum computing and the fact that, like, at the same time, right now, we're doing both the structural development, like making a quantum computer that works, but at the same time, people are working on like algorithm and like the algorithmic of it, and like basically working out the computer science of the quantum, right?
Yes.
And do you know, in the history of like the classical computer, the silicon chip and the silicon computer, when people were developing the silicon chip, do you know if they were at the same time also working on developing the computer science around it, like doing both tracks in parallel? Is that the same? Have we done the same thing twice?
No, I don't. So first of all, I think there's at some point people start to develop in parallel. But so we can see here, so field effect transistor was proposed. This is just single transistor, and it's like literally like this big, like one transistor like this big, 1 bit, right? So it's like 1947, and not until after 25 years we have this 4-bit, and this is just 4-bit. So at that point, I'm what I imagine is there is no way people are working on software. But however, I would like to point out Turing machine, this Turing test was actually proposed in 1936. And after like 10 years or so, 8 years, 9 years, they already have some mechanical computer or like vacuum tube computer based on the Turing machine.
Yeah,
so I imagine there's some parallel work.
Wasn't there the punching cards, right?
Yes,
that they were using for the looming machines and back in the late 1900s.
Yes, they're basically just for typing or some periodic works. They're not not really doing some heavy computational work. But there are already some. I would say there was already some interest in here, but not as not like today. For example, we are very interested in using it. We really want to use it, or like at least software engineer, they really want to use it for their interest, even though we're not even sure like if the gate-based operation is the right way to go. But they already want to do that.
Okay, thank you.
Okay, thanks. This is just like an attempt I am thinking now, but there's definitely some other way to. Yes.
Yeah, I have a small question on this particular workout. What does the size mean? Like the size of the different words? Is it?
So this is supposed to be, if the database is large enough, supposed to be the frequency, like in terms of how many times it show up. But I didn't do. I mean, this only pull out from four different universities.
I see.
So it's not. I wouldn't think that it's that thing, but it's supposed to be that.
Okay. Thanks.
Thank you.
Can I ask a question? So it's because like all this, because most of this quantum computation is more higher population should be in like computer science department or like that. So that's why you kind of, when you search this, then you see more like things will be in the computer science area, not like in our physics department. Like, I mean, just like the population of physics department is lower than the population in the computer science. So I even did not know where's the quantum. I cannot find it. I keep finding that. I kind of, where's the quantum?
So
I didn't see.
I think one important thing is one observation is the hardware is not that we do not have an agreement on which hardware we should be using yet. Right? So each platform has its own advantage. Like for example, NMR system, the oldest one, they're pretty good at this the T1, like the data, how long the data or like how long the information is stored, because they're literally defining the they're the atomic clock, right? And they're literally defining like what is 1 second. So when you're talking about T1, the T1 can be, in our world, in our terminology, we call it the T1 is infinite because they define 1 second. And in our case, we're like in superconducting qubit case is like 100 microsecond or so. So, and the other, but one important thing is how fast the gate can operate. So basically, how the gate operates like that. You have a certain amount of time that the information will be like gone, and if you can operate pretty fast, you can still squeeze in many gate operations. So this is still doable. The whole superconducting qubit is doable. It's basically because of that, because we have pretty fast gate time, so we can do squeezing a lot of gate operations. But there are all other different things like ion qubit. They're also good, and what's better is trapped ion. They're good in terms of connectivity. So superconducting qubit, you just need to connect one qubit to the other one with the real line, right? Drawing a line or something. But in terms of ion trapping, you can actually move the qubit around and just operate it, and you can entangle them and disentangle them easily by operating the electromagnetic field to trap those ions. So they have their own advantage, and these two basically NMR and superconducting qubit and ion qubit, they need very different physics inside, right? So for example, I'm working on superconducting circuit. I know nothing about optics, right? So if I need to learn, I need to decide which. I mean, in terms of hardware, it's pretty difficult. So it's hard for a graduate student within their lifetime to learn different hardwares. Right? So I guess that's one reason why the hardware is still in very academia field, not in the hardware. Not in the industry yet. Yeah. And they're not teaching it because we don't know which one we should be teaching. So now this is the fun part. So how to lower the interest threshold. So for myself, we just play games, right? We make games, quantum games. And in fact, game is not just for fun. There are many other, we're already seeing a lot of examples like Deep Blue in the chess and AlphaGo from Google to create some AI so they can, basically we can use the game to study how the human brain works, how the computer works. And this Microsoft Flight Simulator help the pilots to get used to the navigation without jumping into the airplane. And there's this Peacemaker. It's an interesting game. I never played. I just Googled it and I found this interesting game. It's basically it's kind of a government policy simulators that simulate the situation between Palestinian and the Israeli. So these are kind of educational thing that the game can provide. And the right-hand side is called folded. Basically, it's developed by University of Washington. They are so if player. So the idea is when player play around this protein, they can help to unfold it and teach computer how to unfold protein efficiently. So basically, this there are a lot of different functionality a game can provide. Right? So another thing is game also stimulate the progress of hardware. So here I particularly put a time point here is this 6205 chip that was particularly developed for a game console in 1975. This is when Atari, they first released their game in 1975. So as a home console. And there's another example in 1990s, Super Nintendo, on the platform Super Nintendo, they released the Star Fox, which is the first 3D games. And eventually they because at that point, the Super Nintendo is already released. So in the game console, there isn't any like 3D graphic chip. So what they did is they put this 3D graphic chip into the cartridges, and then they released it to the players. So they buy it and put in, they can play a 3D game. So it's kind of the ancestor of the graphic card, the idea of graphic card we're using now. And so this is also some reason that we are interested in developing some kind of game. They can help to do not just attract people to have some educational purpose, but also we can think of some new applications, what quantum can be used, and we want to improve, we want to guide the development of the hardware development in some direction. Then there are many games out there now. Two of them I would highly recommend can try is so later on I can share this slide if you're interested. And basically this one is a QPOL. It's basically it's kind of just directly implement a quantum computer with QSKIT to mimic the Pong provided by Atari in 1975. And there's this it's called Hello Quantum, and it's available on your app store, either Apple App Store or Google App Store. So it's called Hello Quantum, and what it does is basically you need to there are certain pattern you need to match, and by using the quantum gates. And this is a recent game that I coach in the Taiwan hackathon. There's a like 2 weeks ago, they're using this quantum computer to do some fortune telling things in the traditional Taiwanese Taoism religious things. And one particular game I'm working on now is so basically this is just when I was free, I'm tired of writing things, I just come and do some coding. Right now I'm doing this quantum games. Basically what it does is we're seeing here, there are 3 qubits here, and you can do some operation, gate operation. Basically you do is appending, for example, the red one is X gate, basically it's just NOT operation. So qubit initialized with 0, 0, 0, and by appending one of the NOT gate, it becomes 1. And you can do this. If you do this, you will get 1, 0, 1. And the paddle here will be moved to this particular location. And the task the player should do is just to match the position. Like for example, here you want to append 3 NOT gate here. So you see 3 red block, and it will be 1, 1, 1 here, for example. And the quantum starts at when there are 2 blocks here. For example, you want a system to be simultaneously in 1, 1, 1 and 1, 0. what you do is you put a Hadamard gate at the rightmost qubit. You have 1 1 and 1 0, and in order to prevent player just to put 8 states here. Basically, that's just you have Hadamard, Hadamard, Hadamard. In order to prevent people doing that, I ask computer specifically just do 16 measurement and only like show those states with the measurement counts more than 5. So basically, if you do all of them are like superposition, you will have 2, 2, 2. Ideally, you everywhere have 2 measurements, and there will be nothing. So basically, you will not be able to do that. So this asks particularly people to do this quantum circuits in order to reproduce the state distribution, particularly at these 2 positions, for example. And as the game progress, we want to introduce some more difficulties, for example, entanglement, and they will be doing this work. So if you need to match some pattern here and there, 1 1 0 0 0, basically it's impossible just to use the binary operation and superposition. You need to introduce some entanglement. So basically the state will change accordingly to one of the gates, one of the position. And let me just quickly show you this. I kind of quick version of it. So this game is written by it's written with this Pygame package in Python. Yeah. So the idea of this game is basically want to train the user to know how to operate with quantum circuit to reproduce those truth table. Let's put it this way. So for example, this is doing that. You have this distribution, and okay. Now this is something that I'm not sure I can. Okay. No, I still can't get this state yet. So there are some state that so this is a bad. I didn't do the right catch. I didn't catch it, and this one I'm able to catch it. So this is how you do this. Okay, yeah. No. Okay, so this is a good example because it's simple enough that I can solve. So what we're seeing here is we have this. This is definitely the red block should be put here just to put it 1. And now we want to reproduce 1 0 and 0 1. And this is one example of the so-called Bell state. That so what we're doing here is whenever this is 0, this should be 1, and this 1, this should be 0, and it can be done by this gate operations. Right? So it's like that. Basically, you can actually get some feeling that the idea of this game is trying to train user to have to get a sense of how to reproduce a different state with quantum circuit, right? Okay, so we have a little bit more time. So in order not to confuse you, this has nothing. Those things I just discussed has nothing to do with my internship at IBM. Since I promised Tsung-Chi, I will demonstrate some of my experience, but this has nothing to do with that. What I'm doing in IBM is still working on the hardware circuits. In particular, we want to use Josephson junction to make a resonator. So that's what I did mainly over the summer. Right? And here is just a kind of like attempt because I feel personally I found that this is a really big issue in terms of generation wise. There are a lot of non-equal, at least from where I came from. I work with those operators in the industry. They're all very smart. They're also very smart. They're just not able to handle the mathematics and equations, or like just handle the test, like the qualification exam, for example. And so they have to, or they need to work. They need to get some money immediately in order to like provide support to their family. So they have to work, they have to quit their learning process. And as a result, I would think I'm highly motivated by this attempt just to, if we are able to correct the whole situation from the beginning this time. So we're standing at the turning point where we want to enter the new generation. We're starting a new quantum industry, and we are actually have those tools, these tools, and I would like to make sure we do it in the right way, just by lowering those thresholds and inviting more people to come into this community and to learn quantum information, actually. Okay, so these are my 2 cents. Thank you.
Let's unmute ourselves first, and let's give Vincent for his a big hand to Vincent.
Thank you.
So I guess anyone can ask a question if you want, or say any comments, or just thank you, or like that, anything.
Yeah, I have a question.
Yes.
Your app sounds really cool, and I'd love to try it.
Oh yeah, sure.
Like your game, because like it's really challenging to think of like quantum circuits.
Yeah.
And
with a given amount of
really
time.
cool to like have a Tetris type game of like you have to figure it out and come up on the spot with the gates. I'm sure I would be terrible at it at first, but then get the hang of it quickly. It'd be fun. I just had a comment. You're talking about like apps and like different games that have quantum circuits in it and applications. And I just wanted to say that like not only is there apps that do actually have or games that actually have quantum concepts in them, but there's also a lot of apps and games that use the quantum buzzwords or the idea of quantum wrongly, right? So there's an app recently I was made aware of called Rendonauts, which calls itself that it generates a location on the Earth close to you based on the quantum random number generator, and you have to explore and go to that location. And apparently they claim on their website that if you think very hard about something, it will influence the quantum number generator. So a lot of people are trying to come up with weird quantum buzzwords and preying on the gullible
yes,
to make
yes.
apps like that. So
that's actually, yeah. Oh yeah, go ahead.
It's very easy in technology, right? To put slap quantum on something and then people are going to buy it.
Yeah, definitely. That's one thing that I found. Yeah, I think that's one major problem in quantum games these days. They're actually, so for example, this coupon, take this coupon for example, it actually developed in one of the also from one of the IBM Qiskiters, but he also kind of I mean, this, please don't take me wrong, this is definitely great work, but you can actually beat, if you search this game, you can actually beat it with binary gate, with just binary operation, because it's ping pong, right? And ping pong just have single ball. And
yes.
you need to connect to one single gate. So you can actually beat it with gate only. You are able to come up with this, and that's the one of motivation. Actually, this is the inspiration point. I play this game, and I noticed that you don't need quantum mechanics. you don't need Hammer gate, right? You don't even need Hammer gate. You can beat it because this is, yeah, it's just a single point. You don't just need to collapse your quantum state into single point.
Yeah.
You don't need the rest of the thing.
Yeah.
And that's why I come up with this idea. You need at least 2 blocks, and you simultaneously take those blocks. And you cannot overuse it. You cannot just use a bunch of Harama gate and then collapse into, and then get like eight states. You cannot do that. You need to introduce some idea of measurement. You need to collapse, and I set up some criteria. If you only measure twice, it doesn't count. And that's how I eventually come up with this idea. And I totally agree with you. Not even just in quantum games. There's a lot of quantum those new startups, quantum startups.
Oh yeah.
They're actually not that. They're just slamming buzzwords and then get money from investors. That's very true, and also attracting new employees. So I was advised that if you really want to jump into this industry, we really need to like look into that. If you want to set it as a career, we need to be very careful about that. And for myself, I personally just want to do something like really has some sense of quantum. And because I'm doing this with my free time, so I have no pressures. I still work as a I still work with quantum hardware. I have my jobs, I have my research, and I'm not getting money from those things. So I have more free time to do something real. I think is real quantum, and then introduce more ideas so people will enjoy. Yeah, that's my. But I totally agree with you. There's a lot of weird things going on.
Yeah. Well, thank you.
Thanks.
Great talk, Vincent. Thank you.
Thank you. Yeah, I can share my. Actually, I can. You all can see the chat box, right?
Yeah, Vincent, you can share. I mean, you can give your.
I have a GitHub. I have a GitHub. Okay, yeah.
To the SBAR website. And that's
you can put Tsung-Chi, you can put a link on the website, right?
Yeah, I can do it. No problem. So Vincent just later.
Oh, okay, great.
I just put it down.
Like it or not, I can share my. I put it on the GitHub, so you can just download and use it.
Yeah, or just give me the website. I mean, anything. I can put it on SBAR and people can see. Yeah. Go ahead if anyone else have any comments or question.
So do you think if you had access to a quantum computer, you could beat one of these quantum games more quickly than sort of manually putting together the gates?
Sorry, you mean beat this game? So what I'm not quite sure what do we mean by beat these games?
Or like do better in the game, succeed in the game?
Oh, well, I mean, if you succeed in this game, you're able to come up with. So basically, this game is literally just try to train a. So in classical, if we make a parallel, if we make an analogy to classical, we're actually designing some gates that can do a certain state distribution, and that's in parallel to this Verilog language that eventually classical computer came up with. So you have a gate, and you want to from the gate operation and or not, for example, you want to put together and, for example, do some plus, like A plus B out of these operations. And this is one of the example. So you need some operation to put together to generate a Bell state. You need some operations to generate a GHZ gate. But none of this, at least not in my game, none of this will be benefit from, all you need is just a classical simulator, a quantum simulator. You don't really need a quantum computer. There's not faster or something like that in this game, but there's probably some game that can benefit from playing on a real quantum computer. Did that answer your question, Clement?
Yeah, I was just thinking it would be fun if you could make a quantum game using a quantum computer too, and then compare the classical one.
I was actually thinking that, and I think one thing will be very different is the error. So like the error mitigation, and that's one thing that we can probably think of, because error mitigation doesn't happen on these quantum simulators. So in terms of error mitigation, it will be T1, T2 dependent, and maybe we can do something about that. Like, so you have different, so every time you assign with a different qubit, real qubit with a real T1 and real T2, and it will show you T1 and T2, and maybe you need to do something in a given amount of time, or within, you need some knowledge about T1 and T2, and you can play around with the, that is one thing that would be interesting, yeah.
Okay, so now it's about 7:30. So for those of you who want to stay, yeah, you can stay and chat a bit. And if not, thank you all for coming. And next week, we still have SPAR, right? Next week, we have Anna Helene in high energy theory. So today is the only high energy, today is the only CMX. Next week is the only high energy theory. And she'll give us similar talk and about her paper about color physics. So yeah, please come if you have time, and thank you so much. So thank you so much. Go ahead to your dinner or anything you want.
Thanks, Vincent.
Thank you.
Thank you.
Thank you, Vincent.
Thank you.
Great job. Great talk.
Pleasure. Thanks.